Let's have this given item here, and we are to verify the result of this integral using Green's theorem in the plane. Take note here, we have the integral of the contour path C of these functions, but strictly bounded by y is equal to x squared and y is equal to square root of x. So the first thing we need to understand here is, of course, the equivalent form according to the Green's theorem. Double integral of your region R of your partial derivative of your q function with respect to your x minus the partial derivative of your p function with respect to y. You have your dx over and dy. As for this, it's up to us later on if we're going to stick with that or rearrange these two depending on the region that is bounded for both x and y. And that's the first thing we need to understand here. Okay? When we talk about these two boundary here, they are both curves. Allow me to just have a draft here. Okay, so if we're talking about y is equal to x squared, we know that it's in a parabolic curve opening upward. So let me just assume that my graph here is appropriate. That's for our y is equal to x squared. But for y is equal to square root of x, it's actually a parabolic curve opening to your right. Okay, so it's opening sideward in this form. Again, let me just assume that my graph is appropriate, just like that. The region that we're talking about here is this region here, bounded by those two curves. Okay, so this is different from the previous two examples, speaking on specific regions which are actually square and rectangle in nature, where we are given with the exact boundary for your x and y. At this time, we need to identify the boundary of our x and y. Now, we can actually use here systems of equation, or by substitution, since y is equal to x squared and y is equal to square root of x. Meaning, if we're going to square both sides for this, that's actually y squared is equal to x. Let's try to substitute here. Y is equal to your x, which is y squared, which gives us y is equal to y to the power of 4. Solving for y to the power of 4 minus y is equal to 0. You will have here y times y cubed minus 1 equal to 0. We're solving the values for your x and y here, so let's just continue. Y can be 0 and y cubed minus 1 can be 0. Y cubed is positive 1, so y is also positive 1. These are the two values of your y. Substituting that anywhere here, or allow me to use that here, or let's say since it's y is the given, let's try to substitute that here. So for your x, we are going to square the y. So for our y is equal to 0, our x must also be equal to 0, or 0 squared. For our y, which is 1, our x is also equal to 1. In short, our points here, basically the intersection of the two curves, I'm talking about this area here, and of course the origin 0, 0, okay, this one here, okay, and the intersection at the top is actually at 1 and 1. We now know that the boundary for your x and y are actually from 0 to 1. As you will see, our x changes from 0 to 1, and our y changes from 0 to 1 as well. But do we use that specific boundary? Because similar to the previous example when we talk about the rectangle where x is from 0 to 1 and y is from 0 to 2. But this time, it's not a rectangle, it's just a curve. It's a boundary, or it's a region bounded by those two curves. So what can we do here is this. Look at our given functions, y is equal to x squared and y is equal to square root of x. These two are now the boundary for your y. So y is between any of those two. Looking at our graph, vertically, the graph at the top is actually the parabolic curve opening sideward, which corresponds to square root of x. That's the upper boundary for your y, sorry. For your lower boundary, it's the curve of which is the lower boundary, lower boundary of the region. That's actually your x squared. we can see here that our y is expressed as x squared to square root of x. It's not 0 to 1, even if the value for your y is 0 to 1, because that is the indication that our region is not anymore rectangle. It's a curve. But as for your x, it's very obvious. It's just 0 to 1. Okay? This means that our graph here, or our region, bounded by these two curves, is simple horizontally. Okay? So our x is very specific, 0 to 1. As for our y, expressed as x squared to square root of x, depending on the value you're going to try for your x. Okay. So what is the indication for this? Since it's x, which is easier, we will have to interchange this. We will have to use dy over dx and dx. Okay? Because dy, as soon as you will have the region for your x squared to your square root of x, it will still be simplified later on, as we will have the outer integral in terms of x, 0 to 1. Because if we're going to stick with the original or written here, let's say dx and dy, as soon as you will apply the boundary for your x, it will apply 0 to 1. And that's good. But once you will apply here the next integral, which is the outer one, x squared and square root of x will still appear as it's the region for your y. Okay? So we will have that. Again, we will apply here dy dx. And of course, the integral here outside would correspond to your x 0 to 1, and your inner would be x squared to square root of x. Our goal first here is to identify this expression. So we know that in our given expression here, our p of xy function is the function multiplied to your dx. So that's actually x squared y. And for your q of xy is this function here paired with your dy, 2xy squared. Now, let's solve first the individual partial derivatives with respect to individual variable. So the partial derivative of your q function with respect to x is the partial derivative of 2xy squared with respect to your x. Okay? This means that y here will be treated as constant. So in terms of x, this is actually equal to 2y squared. Am I right? With respect to x. Okay? So x would be our variable. Yeah, that's 2y squared. For our second partial derivative, okay? So the partial derivative now of your p function with respect to y, our p function is actually x squared y. But now with respect to y, treating x squared as constant. So with respect to y, that's just x squared. These are now the items we need to plug in here. So allow me now to use the correct double integral form, and probably I might be using some additional spaces or pages later on. So again, the outer boundary for your dx is 0 to 1, and the inner is for your y, x squared to square root of x, of the difference of the partial derivative of q with respect to x and partial derivative of p with respect to y. 2y squared minus x squared, and again you will have to have dy and dx here. Okay, so let's start with this integral. Allow me to place that here. So we will treat this later as the outer integrals. So for this, treat with respect to y, so the x squared here and 2 would be constants. So by linearity property, you will have to 2 the integral from your x squared to square root of x of your y squared dy, minus, again, x squared is a constant because it doesn't have any y, x squared, the integral from x squared and square root of x of your dy. This would be equivalent to, by the way, since this would have functions, so allow me to move here. That's actually 2, and then the integral of y squared is y cubed over 3 of x squared to square root of x, minus x squared, integral of dy is y, x squared to square root of x. don't worry about those y's, because as you will apply the boundaries, all of your variables later on will be x. And again, it will only be used for your y. So here, you will have 2 y. Your y cube is actually, so just like what I have mentioned, I might need some spaces. So yeah, that's actually 2/3. So your y is x squared cube. Sorry, upper boundary. So that's square root of x. Okay, cube, right? Minus 2/3. Your y would be x squared cube. The second one, minus x squared. Let's add here grouping symbol because it's preceded by a negative sign. Your y is the upper, square root of x, minus x squared times x squared. So you will have here 2/3. Take note that x, or square root of x, is actually x to the power of 1/2. Okay, so this is actually 2/3 x to the power of 6, loss of exponents. You have here x squared again, so x to the power of 1/2. This is x to the power of 4. So this again, 2/3, applying the loss of exponents, x to the power of 3/2 minus 2/3 x to the power of 6. Take note this is 2 plus 1/2 or 5/2. So you have x to the power of 5/2. And you have here, sorry, this should be plus because of double negative property. That's why I had grouping symbol earlier. So plus x to the power of 4. Okay, so none of those terms can be combined. So allow me to copy this now and add another page because I don't have any more usable page. And of course, allow me to also copy this double integral here because this is actually, or the red one, the red text is just the result of the inner integral. Okay, so when we apply that here, from 0 to 1 of your expression, 2/3 x to the power of 3/2 minus 2/3 x to the power of 6 minus, sorry, x to the power of 5/2 plus x to the power of 4 dx. All of the terms now have x's. So applying now the linearity properties, 2/3 integral 0 to 1 x to the power of 3/2 minus 2/3 integral from 0 to 1, sorry, my bad, this should have dx. Have I applied it earlier as well? dy, alright, that's correct. So linearity property minus 2/3 integral from 0 to 1 of your x to the power of 6 dx minus integral, because we don't have any constant here, 0 to 1 x to the power of 5/2 dx, and of course plus x to the power of 4 dx from 0 to 1. Okay, so we'll have here 2/3 of x to the power of 5/2 because plus 1. Okay, all of these are actually integral of u to the n du. So n plus 1 over n plus 1, we know that, right? But don't forget the boundary from 0 to 1. Next, 2/3 x to the power of 7 over 7 is 0 to 1. This one here, so 5/2 plus 1 is 7/2, right? X to the power of 7/2 over 7/2 is 0 to 1. And this one here, x to the power of 5 over 5 is 0 to 1. Before we substitute the boundaries, allow me to simplify these nested rational expressions. So 2/3, reciprocate that, 2/5. So 2/3 times 2/5 is 4 over 15. X to the power of 5/2 still is 0 to 1. I haven't applied here the boundary, just simply simplifying the nested rational expressions. This would be minus 2 over 21, right? 7 times 3. 2 over 21, x to the power of 7 still 0 to 1. This time reciprocate that. Yeah, minus 2 over 7's x to the power of 7/2 still 0 to 1. And still here you have here 1/5 x to the power of 5, 0 to 1. Now, applying the boundaries, this is 4/5. You have here 1 to the power of 5/2 minus 4/5 times 0. If your terms are preceded by a negative sign, make use of parentheses. It might not be needed here because the lower boundaries are 0, but just to be consistent, let's have grouping symbols. You have here 2 over 21, 1 to the power of 7, minus 2 over 21, 0 to the power of 7. I mentioned not necessarily needed because that's automatically 0. But again, to be consistent with what we did, let's have that. Again, second grouping symbol, 2 sevenths, 1 to the power of 7 halves, minus 2 sevenths times 0 to the power of 7 halves. And the last term, since it's plus, no need for grouping symbol, plus 1/5 times 1 to the power of 5 minus 1/5 times 0 to the power of 5. So again, remove all those zeros. So you have here 4/5 minus 2 over 21 minus 2 over 7. You have here plus 1/5. Now about this one, LCD. 21 is 7 times 3. So I need 7 and 3 times 5. So 35 times 3 is 105. Right? LCD of 5, 21, and 7. Right? Because this is actually just a short review, 7 times 3. So we'll have here 7, 3, and 5. So that's 105. Just a short review. So 105 divided by 5 is actually 21 times 4. So you have 84. Sorry, my bad. I made a mistake here. That's actually 4 over 15. So 4 over 15. So still, I have here 15. This is actually 5 times 3. So basically, same thing. You have your LCDs here. Okay. That's why I am very confused with what my process is. So now, it's correct. Still 105 for your LCD because you have 5, 3, and 7. So 105 divided by 15 is 7. Yeah, 7. 90 plus 15. 7 times 4 is 28. Next, 105 divided by 21 is 5 times 2 is 10. So minus. 105 divided by 7 is 35 minus times 2 is 105 70, that's 10. 35, 15 times 2 is 30. Okay, my bad. And 105 divided by 5 is 21 times 1 is 21. 28, 21, that's actually 49. So you have here 9 over 105, still divisible by 3. You have here 3 over 35. And yes, this is the final answer. This is the result for the integral in this given function here along the path or the region bounded by y is equal to x squared and y is equal to square root of x. And this has been verified using this Green's theorem in the plane. Again, our answer is 3/35. The answer for this item here, 3 over 35. So please review this on your own time. Thank you very much for watching.